Hello, chemistry. Happy Thursday. Buckle up. We're going to go through the last part of bonding today to get you ready for your quiz tomorrow. As such, I won't have an assignment for you today, but I will giving you guys a study guide. You guys will be able to use a note card on your quiz tomorrow. Your sub will have those available for you. So, sorry once again that I'm not there to answer your questions. If you have any, please email me. Let's jump right in. Give you guys the most time possible. All right, so we've talked about covalent, we've talked about polar covalent, we've talked about ionic a little bit. You guys did some Vesper work yesterday. Ionic bonds and compounds are made of ions, which are negative and positive ions. When they come together, we have a neutral molecule, or not molecule, excuse me, compound. Compound because it's a ionic bond. Molecules are for covalent. So these charges, this plus and negative up here, will cancel out, and this will be a zero charge compound. Most ionic bonds will form crystalline solids, such as the crystals of table salt are made out of ionic bonds. And if you get down really, really small, and I have a picture coming up, you can see those tiny little crystal structures. A crystal itself is of any ion or ionic compound is going to be this three-dimensional network of positive and negative ions that are mutually attracted to each other, that are going to have these pluses and negatives equal out to zero. And next chapter is all about, that's what we're going to be doing. We're going to be balancing chemical equations and doing all kinds of good stuff there. So a formula unit is the simplest collection of atoms from which a compound's formula can be established. So one formula unit for salt is NaCl, one sodium, one chlorine. Very rarely do we see this in nature. There are usually thousands, if not millions, like in your shaker on your table, of these guys together. But the simplest is just one sodium, one chlorine. Some ions exist naturally as a 2+ or a -2 charge, and these charges must be equal to form an ionic bond. So magnesium, very commonly magnesium being in that group 2, we want to get rid of 2 of its electrons. Gets rid of 2 negative charges, it will get 2 positive charges. You guys have seen chlorine already. In the case of sodium chlorine, where sodium had 1+ and chlorine canceled it out with 1-. This chlorine is still 1-, but now we have 2 of them. So we actually have 2- because there's 2 of these guys. So this molecule, MgCl, still balances out to be 0. And you guys are going to be experts at that next chapter. But it's just important to mention that and kind of start those gears turning now. So the same reason that we get covalent bonds, which is to reduce potential energy, these ionic lattices are the same thing. This structure is very stable. Inside of a sodium chlorine kind of lattice here, 6 of these chlorines are on this positive sodium, and 6 of these sodiums will be around a single chlorine. So it's this nice lattice thing. Lattice energy, when we had bond energy, lattice energy is the energy released when 1 mole of an ionic crystalline compound is formed from gaseous ions. So as this comes together, it releases energy, forms this nice stable molecule. Metallic bonding is unique. It's not like ionic or covalent. This is the attraction of positive ions surrounded by mobile electrons. So we'll have these nuclei of metals all together, and these electrons, I'm going to draw them in red, little guys, will be just like zooming around the outside of these guys. This is why metals make such good conductors. Remember that electricity is just E- electrons moving through a wire. The same E- is ending up over here. And so they are good conductors of heat, they're good conductors of energy, they have low ionization energy and low electronegativities. they have lots of these free electrons that they're just willing to give away. Magnesium, which is a alkaline earth metal, wants to give away 2 to be a 2+. Wants to give away 2 electrons, so there's 2 right there. Iron can form iron either 2 or iron 3+, where it wants to get rid of 3 electrons. So we see lots of electrons in the metals wanting to be given up. So because of this configuration and this behavior, metals form into desirable shapes. They're malleable, which means that we can beat them with a hammer, we can roll them, or any other kind of physical pressure, and they will form different orientations. They're ductile, which means we can draw them out to form wires like copper wire. And they're lustrous, which means that they reflect light at many wavelengths. They're reflecting these electrons back out at different wavelengths. Now, the 3 main types of bonding are metallic, ionic, and covalent. Intermolecular forces are smaller than that. These are the forces of attraction between molecules, molecules that aren't held together already by bonds. So they're weaker than bonds that form atoms together. So they're weaker than these ionic, these covalent, and these metallic bonds. There's a couple we're going to talk about. The first is dipole-dipole. So in this, these are equal but opposite charges created by a short distance. So there's a slightly positive charge to this side of this hydrogen chloride and a slightly negative charge to this one. Remember that these little guys mean slight charges. So what that means is this slightly negative chlorine is attracted to this slightly positive hydrogen. Not enough to form a bond, like these solid lines are actual bonds of shared electrons, but enough so that these guys kind of orient themselves in space so that they're close to each other. The direction of the dipole will be shown by an arrow, so sometimes they'll go like this, and they'll go slightly positive, or they'll go the other way, and they'll go slightly negative, depending on what they're trying to show there. But dipole-dipole means that these slightly positives are attracted to these slightly negatives. A specific type of this, which is hydrogen bonding, is coming up next. But dipole-dipoles occur in polar molecules. So this is in our perfectly covalent bonds, these dipole-dipoles aren't going to exist. The negative of one is going to attract the positive of another. We looked at HCl before, and we saw that happening with one bond. In H2O, we can get lots of dipole-dipoles. We get them in these form of hydrogen bondings. So dipole bindings that involve hydrogen are called something special. We call them hydrogen bonds. And this is between a hydrogen and an unshared, remember these little unshared electrons on these oxygens from our Lewis structures, electrons on a strongly electronegative atom. So these are going to be atoms in that top right, not the noble gases, but the top right corner of the periodic table. So this is going to be things like fluorine and oxygen and nitrogen. Remember that fluorine is our most electronegative, so yeah, they're really going to like him. And oxygen they really like, and nitrogen they really like. So these high electronegative differences, these polar covalent bonds, make these bonds highly polar. Usually this one is drawing them in red, but usually between them, I have a water molecule here with these unshared electrons. We'll draw these bonds like this between this H of this water molecule. So these ones, covalent bonds. This one in between molecules is our actual hydrogen bond. Our last one, and our last slide for today, is on London dispersion forces. At any point in time, the universe is in motion. Atoms themselves are constantly moving. At any point in time, there is some random things going on the atomic level, which is kind of beautiful in its own little majestic way. So these constant movement of these electrons and these constant things of these forces going back and forth, at one point in time, we always think of them, cells as this first configuration cells. Atoms in this first configuration, where they are just, all of these charges are perfectly balanced. They're all equal distance from the nucleus. Just a happy little atom. Unfortunately, that is very rarely the case, or it happens very, very, very quickly, and then it very, very quickly doesn't happen. But what will happen sometimes is sometimes all of these electrons will end up on one end of the atom. And we have this temporary, very small negative and positive ends now, these dipoles. But unlike our polar molecules where these are existing like long term, these ones are very fleeting. These ones will very briefly be attracted to each other, and then they will just disappear. So they'll form, they'll go away, they'll reform in a different spot. Maybe the next time that plus is over here, and those negatives are on the other side now of this atom. They're very fleeting. Unlike our actual like dipole forces, these London dispersion are very fleeting. They don't happen for very long. The larger the molecule, the larger the dispersion force. It's the difference between this atom that has 4 electrons and an atom that has 92, like uranium. Should have 92 if it's neutrally charged. There's a lot more movement with 92 electrons than there is with 4. And they're a lot further away from the nucleus, so they have a little bit less of that positive force pulling on them. So they have a little bit more energy. Remember, the farther we go out, the more shells we get out there, the bigger our atomic radii gets, and the larger and more common we have these London dispersion forces. And our noble gases, we haven't really talked about them much, have these forces. You'll find London dispersion forces inside of noble gases. I hope this covers up everything. Nice, tight little bow for this chapter. If you guys have any questions, please email me. You can use a note card, both sides, for your quiz tomorrow. I miss you guys. Have a great rest of your day.